Perfect. Okay, thank you everybody for joining this session on building a carbon impact agent. My name's Darshna Shah. I work as a Chief AI Officer for a AI and cloud consultancy. I'm also a Microsoft AI MVP, so do a lot of things within the community, and it's actually my first time at NDC, so I'm really, really excited to be here with such a vibrant community. So a little bit about my background. So I didn't enter tech in a kind of traditional way. My background's actually in neuroscience. And through the years, I've kind of had various different themes that have really stuck with me. I'm sure like a lot of you, we're very much attracted to a lot of the really complex problems that don't necessarily have easy to fix solutions even. And some of the themes that have really stuck out for me are mapping a lot of cognitive abilities that we have as humans in a computational way. Likewise with cybersecurity, that doesn't necessarily have a right or wrong answer, and it's always a little bit of a cat and mouse chasing game. Today, we're actually going to talk about the third theme that's stuck through my career, which is around energy with technology. And sustainability has kind of really often been posed as kind of either this villain or savior. And I don't think that binary kind of narrative really fits. So that's what I'm going to focus on today. I'm going to provide a bit of the macro picture around the new narrative that's being shaped in energy and technology, how we can actually implement sustainable AI design, and a lot of the power in terms of the scale of the problem that actually we have at our fingertips. And we'll look at how we can actually start implementing some of that sustainable AI design through building a carbon impact agent, monitoring a legal PA agent, using LangGraph. So I know we're big .NET developers in this community. My language of choice is Python, but I'm sure there'll be a lot of crossover. So why should we care? Greenwashing is fundamentally cemented within our society. We see a lot of enterprises that are making these really bold statements around decarbonisation, achieving net zero, even net negative in terms of that. And that's really conflicted with a lot of the headlines that we see around greenwashing. This can be quite discouraging when we're trying to kind of make a little incremental step forward. There are also recent power shifts, so a lot of the geopolitical movements that are happening in terms of big tech really owning a lot of the supply chain is really fundamentally, in some cases, quite concerning, in some cases threatening our fundamental pillars of society, things like democracy. But as I mentioned, there is this new narrative that's forming that we can kind of see through market trends. And the future of energy and tech are really fused together. And it's actually quite interesting when we look at some of those market trends, how much of the power we would actually have to influence what the future looks like. So before we get into it, I just wanted to cover some of the energy-specific AI advances. And as I mentioned, a lot of AI can be used to enhance our movement towards sustainability, but it's not a silver bullet. It's not going to be the answer to all of our problems, specifically within the climate change challenges that we face today. So if we look firstly at supply chains, obviously with more and more data at our disposal, we can look to better forecast trends, weather patterns that enable us to really understand our customer base and demand. We can look to implement AI for predictive maintenance and optimizing manufacturing. There's obviously route optimization in there, and even just building more resilient supply chains. We can understand which suppliers are likely to be affected by different geopolitical or even climate disasters that may need us to look a little bit further in terms of who else could we procure from. Designing and planning cities. We're going to go a little bit into the supply chains of data centres, but if we're looking a little bit further afield at smart cities and renewable infrastructure, there is a lot of optimization that we can build in using AI that not only optimize for the value of the asset, but also the operational longevity and maintenance of those assets. Materials is a really interesting one. Did any of you follow the story around AlphaFold? No? Okay. So it's a DeepMind kind of creation, but ultimately they changed the way using AI the acceleration of which we can fold proteins. So AlphaFold specifically led to a 45,000-fold acceleration in drug discovery. What does this mean for us? When we're thinking about synthetic fuels, high heat temperature heat storage, desalination projects, long storage batteries, decarbonised cement, even new plastics, and even nuclear fusion, this could have profound impacts. So just to put this into perspective, the International Energy Agency highlighted that only 0.01% of new next generation solar PV materials have been experimentally produced. In addition to that, 1% of energy patents reference AI. So that really puts into perspective the untapped scale and potential of opportunity we have there. Transport. So obviously we've probably seen a lot of the EV technology that's evolved over the last few years, but beyond kind of optimization of fuel and predictive maintenance, we're also using AI to test autonomous vehicles. Obviously, the risk profile is quite high, so we want to make sure that obviously has human in the loop. And then security. Cyber attacks on energy utilities have increased by 3 times over the last 4 years, and that scale and quality has been enabled by AI. Some examples of this are in Ukraine in 2015, 225,000 people were affected by the blackout. In Mumbai, which is the financial centre of India, a similar energy utility attack led to a big outage in 2020. And the one that we're kind of probably most familiar with is the Nord Stream pipeline sabotage of 2022, where if we had satellite sensors in place monitoring those assets, we could detect anomalies and potential sabotage up to 500 times faster. So a lot of really impactful potential there. So what is the macro picture looking like? What is happening more broadly in terms of what's being financed and what's not? So if we look at the trend there, we can see over the last few years, AI investment has significantly increased. Just from 2024 to 2025, we've seen almost a 40% jump, especially in 2025. So that was $202.3 billion that were invested in AI, which was on par with the rest of funding in total. And if we look at how that investment was spread, we can kind of see a lot of that investment was going to the big frontier firms. OpenAI, Anthropic were sweeping up billions and billions of pounds of that funding. But what really remains to be questioned is, will these leading model developers continue to raise billions to address their voracious appetite for compute power, or will it be met by partnership gaps? So ultimately, there is no AI without energy. There is an extremely complex supply chain underpinning delivering AI to us as a globalized society. And what we can see is that energy demand is set to increase. So demand growth for data centers accounted for 1.5%. That's 415 terawatts of global electricity consumption. And that's shown 12% increase year on year since 2017, which is 4 times faster than the total rate of electricity consumption. And this is set to increase by 2030 to 945 terawatts. And that's slightly more than Japan's total electricity consumption today. In terms of investment and top deals, we've seen similar trends to what we've seen in AI. So there are bigger checks written for fewer players. Nscale and Crusoe, 2 big data center developers, swept up billions in a lot of that investment funding. Likewise, for nuclear fusion companies, a lot of that investment is going there, which is critical to kind of supply the next generation of data center development. Regions. So the US continue to lead in terms of their data center footprint, accounting for 45% of global data center electricity consumption in 2024, followed closely by China at 25% and Europe. So whilst these big 4 hyperscalers are kind of leading the way in terms of low carbon data centers, there is really a lot of challenges that they face in some of these regions that currently dominate, which are leading to other areas of the world becoming a lot more prominent in their role within the supply chain. So just a few days ago, I was reading around some really prominent data center development that was happening in Italy. So supply chain, obviously our electricity demand is going up and up and up, irrespective of just technology. Us as a society are consuming a lot more electricity, and as our population increases, our infrastructure is going to become more and more challenged. So this congestion and stretching of supply chains has led to there being a projection that 20% of the new data centres that are due to be developed could be at risk of delay. So that's going to require a really close collaboration between technology and energy and how we bring the two together in order to overcome those challenges. So the shift in power, tech is owning the upgrade. As I mentioned, the supply chains in data centres are extremely complex. We're relying on a lot of really rare critical earth minerals that are being used to supply components to build the data centres. GPU chips being prominent ones. There are really complicated lithography machines required to kind of etch these kind of transistor imprints onto these silicon wafers, and that can range in millions and millions of pounds. And that's just one component, not taking into consideration the networking, the cooling, all of the other things that would go into logistically planning and designing an efficient data center. And then we've got the AI training, which, as we know, consumes a lot of energy within itself. Lots of data that needs to be processed before we can make it generally available for predictive AI, IoT devices, computer vision, and obviously generative AI being the big one. But the manufacturing process itself actually only accounts for a really small proportion of the entire electricity demand from data centres. It's actually the operation, as you can see here, that accounts for the majority of our electrical consumption. And this is what I was kind of alluding to around where the control really lies. And it's more on that downstream trajectory, which we'll come on to in a little bit. But out of that small slither that relates to manufacturing, the majority of that is related to the GPU manufacturing and also server storage. So I said tech is owning the upgrade. There's generally a lot of speculation where data centres are being developed as to what that does to local energy utility bills. So this independent study had a look at a few different areas, and for a typical 100 megawatt AWS data centre, they found that there was a surplus contribution of around $3.4 million, which obviously can be used to modernise a lot of the infrastructure. In the US specifically, the infrastructure is ageing. 70% of their grid infrastructure is 25 years old or more, which requires significant, obviously, upgrades. So in Northern Virginia, often referenced for data center capacity, this study particularly showed that local residents paid 10% less in comparison to the national average. And those larger users were actually covering 9% of those costs. That covers carbon. It doesn't touch on water though, which we'll come on to in a little bit, and is a little bit more complicated to account for. So what is the driving force? I mentioned that we are consuming AI at an enormously fast pace. In 2020, around 15% of firms were saying that they were using AI. In 2024, that's grown up to almost 40%. And it's not just large enterprises. So up to 40% of general online populations as diverse as India, Brazil, Indonesia are also saying that they're regularly using generative AI. And I mentioned the training. So training obviously is very energy intensive. GPT-4 took around 14 weeks to be trained and demanded around 42.4 gigawatts of energy. So this is equivalent to around 70,500 households in the emerging market. There are new contenders to that. So DeepSeek caused quite a disruption to our markets, as we saw, and they actually take on a different model architecture, which relies on a mixture of experts, which means that it's less energy intensive for training certain parts and even consuming certain parts. But the thing I want to highlight here is that efficiency is both a hardware and a software problem. So the cloud wars have definitely gone green. The big ones, Meta, Google, Amazon, Microsoft, are all 100% renewable. But they're not, whilst they're leading in sustainability from that perspective, they typically diverge in transparency of water usage and carbon offset practices. And we'll come on to that in a little bit when we actually start to think about how do we measure this, and what are the traditional tools that are currently existing there. So I mentioned I come from a data science background where we were typically experimenting and developing those models prior to using them off the shelf. And when we were looking at things like this, there were a lot of tools around that we could use, which I will go on to show you, but they haven't quite kept up with the new types of data that we need to measure adoption. So far, we've been talking a lot about the upstream kind of areas. What's going on in the data centers? Yes, they consume a lot of energy to train these models. 5.4 million litres of water for GPT-3, 552 tonnes to train it. Data center expansion is obviously increasing. And there's been a lot of effort into how to make that more renewable. These big tech vendors definitely know that there will be a lot of challenges, especially with our growing climate challenges. But ultimately, if we can crack that, it does unlock a lot of those capabilities of what we can do with AI to push ourselves even further forward. What's not so well documented is what about the downstream applications? How many of you are using AI within a lot of your development processes today? Yeah, most of the room. And do you guys think in that process, you think about kind of efficiency from a carbon perspective of consumption? No? Okay. So I work in consultancy. I've spent a lot of time in the last few years within the legal domain. And there is a lot of FOMO going on. Everyone wants to not be left behind. And that kind of resonates in strategy being developed that focuses on what we want to do, why we want to do it, but doesn't necessarily filter down into how we're going to do it. So when we do get to the how, a lot of the savings from an energy perspective tend to be byproducts of choosing a smaller model, a cheaper model, and measuring carbon consumption doesn't really come into it. But even if we just started there by measuring our carbon impact, it could actually lead to better performance and better profitability from a lot of these AI applications. We could start caching responses, scheduling workloads, and developing better prompts that are a bit more efficient. So this is Microsoft's Azure well-architected framework for developing generative AI solutions in a responsible way. And what we'll see is a lot of the practices actually are what we would do to try and get good results from our AI development anyway. So the two go hand in hand. It's not necessarily dramatically changing the way that we work, but I will go through in each of these components: model selection, model improvement, model evaluation, and model deployment. How can we look at how we can develop more sustainably through all of these? Ultimately, not only are we looking to increase performance from our AI applications, but it will lead to a reduction in power, increase in efficiency, better code quality, and obviously, naturally, a reduction in cost, which I'm sure is music to all managers' ears these days. So model selection, where do we want to begin? Is AI even needed? Is the first question I always start asking. So as I mentioned, I was working in machine learning prior to the release of GPT, and we started consuming a lot of off-the-shelf models. And obviously there is a lot of FOMO going on, and everybody is scrambling to use every single model off the shelf, understand how it performs relative to others, and have that competitive advantage. But we've also seen a lot of AI slop being generated. We definitely see that through over-reliance on these kind of LLMs to generate our code for us. And often that can be not the most efficient code, and definitely needs to be looked at again. But when we have decided that AI is actually needed. Where do we go from there? There are some other practices that we need to think about. So if we want to use AI to kind of automate repetitive rule-based tasks, manage multi-step complex workflows, performing high-volume information retrieval and summarization, and even scaling, all valid use cases for AI, helps us do a lot of the boring stuff. Where we don't want to use AI, and this was kind of touched in the keynote earlier, is around our appetite for risk. So if we are implementing solutions that have irreversible, detrimental financial decisions being made, that's not the level of autonomy we want to give AI agents. If we have poor quality or biased data, it's the same with machine learning, garbage in, garbage out. We don't want that to cascade through to our production environment. There's a lot of use of synthetic data being used to overcome some of these challenges. Have any of you used synthetic data in your AI development? No, not so much. It's something that we've been exploring with, and from a machine learning perspective, we would always say 10% was like a general rule of thumb. It should be used to augment, not to replace. And I would say that would follow through into this, because any assumptions that are kind of baked in to that synthetic data are naturally going to propagate through your development process. And then it becomes harder to pinpoint why is something performing the way it is. Any task requiring empathy or human nuance, so life and death medical decisions, legal judgments, and social care, all very, very human nuanced decisions that require a lot of understanding of different components that are very complex and not really something we want to offload to AI. Where we have inaccurate standard operating procedures, again, these errors compound. So if we are designing an AI solution and we don't understand the entire workflow as it is today, then again, a lot of assumptions are going to be baked in. Without the right gate checks, this can obviously compound as well. So model leaderboards. Hugging Face have a huge amount of leaderboards. Do you guys use the Hugging Face leaderboards a lot? Yeah, a few of you? Okay, brilliant. So this is the Hugging Face leaderboard for the carbon usage of different models. And obviously, that's not always our first and primary objective. We're not always thinking about how is this the most efficient. We want performant results from our AI. And what we'll typically see is that there is usually a sweet spot between using something that's maybe a use case or domain-specific model versus something that is also energy efficient. So we've got through to the point where we've established that we need to use AI. We've maybe looked at a few models that are performant for our use case. We're still not getting the results that we need. So we'd probably evolve to kind of maybe try some fine-tuning and potentially even custom builds. In a lot of proprietary domains, this was tested quite early on, but it's something that we need to think about a little bit more thoroughly. And I'll go on to talk about some fine-tuning techniques in a moment. But I just wanted to highlight this particular paper, which was around Bloomberg GPT and talking around the kind of investment that was needed and the infrastructure that was needed to do this. So to train Bloomberg GPT alone was a $2.7 million undertaking. And it took 53 days of compute running on 64 servers containing 8 NVIDIA 40GB A100 GPUs. So managing that entire infrastructure just for the training alone is a huge responsibility. And then we have to maintain that, keep it up to date, which can be an extremely complex process. We really need to begin to question, is our investment leading to the return that we're expecting? Or is it just a nice credibility to kind of push us forward from a marketing perspective? So model improvement. This is probably a common trajectory that a lot of you are familiar with. We typically start with improving our prompts. We go to RAG, augment with data, then we look to fine tune, and potentially a few of us might look to do a custom build. As we kind of mature through this evolving pipeline of maturity and complexity, we see that we'll typically go from a cheaper solution to more expensive, but that's clearly rewarded with generally higher quality results. But there are some additional things that we can do. So the data layer design, again, from a machine learning perspective, we spent a lot of time cleaning our data, understanding the problem, enriching the data, engineering features before we even started iterating through applying algorithms, testing the performance, and then putting into production. And I feel this is still a key challenge for a lot of businesses, is to get the data in the right kind of quality, understand where the gaps are. Also around chunking and vector embeddings, there are a lot of different research papers that talk about, for your particular use case, what are the best approaches to use that are often overlooked. And then as we kind of move towards more robust world models that aren't just looking at, does this data system talk to another data system and can I join them, but also enriching that with workflow patterns and decision-making processes that are often in people's heads. So we move towards more graph approaches there so that we can actually capture what systems of record don't. Prompts, agent architectures and tools. So good prompts will clearly define persona, context, the process, templates, and usually evoke some sort of reasoning. The agent architectures, there are lots of different resources that talk about different architectures. I'm using LangGraph, so I'll later on, so I will reference the three that they often talk about, which is a single agent, which is one agent that has a whole bunch of tools. We can have a swarm type architecture, so multiple different agents offloading to each other. And then the common pattern, which is having your supervisor assistant and many different sub-agents that it interacts with, but there is one main supervisor agent relaying that information. And then obviously MCP servers have been a huge topic of conversation over the last year. We can definitely augment capability with MCP servers there. So I mentioned fine-tuning, and we don't want to jump straight to kind of a lot of the expensive approaches that I referenced before, but we can actually look at model architecture. So everyone talks about kind of GPT, which follows a kind of decode-only type architecture. But before that, there are many different model architectures that we could use that were performant for different use cases. So there are maybe other models that we could consider. Quantization, other parameter-efficient tuning techniques like low-rank adaptation. So this is tuning just certain levels of parameters rather than for the entire model. Definitely more energy efficient. And then, of course, we want to bring the users of AI solutions closer to us. So why not get them and use their feedback in reinforcement learning techniques and see what that could lead to. Model evaluation. Do you guys engage in a lot of model evaluation before you go to deployment? No? Okay. So as I mentioned, I'm a data scientist, so this is an area of interest for me, and I've tested a few different ones. Deep Eval, RAGAS. I really like the Azure Evaluation SDK because I think the comprehensive range of metrics it gives you and some of the cool new ways that they're introducing evaluation is quite innovative, actually. So they have AI quality metrics. This is what you'd probably consider as your LLM as a judge. So they're getting LLMs to rate, understand the intent of the solution and rate the generated output in terms of groundedness, coherence, fluency, relevance from a score from 0 to 5. Great, but it's almost like LLMs marking their own homework a little bit. NLP metrics, so these are probably ones you're more familiar with if you've come from a machine learning background. F1 score, Blue score, and Rouge scores are incredibly objective and statistical in nature, but they require us to put a little bit of effort in and actually provide ground truth answers in order for us to generate those metrics. I will say that some of the complexity around this can be quite interesting. I think this is the level of, if you're looking at this level of performance, it's where we would probably start pushing towards fine tuning. Because if we take the example, it is cold outside, the Rouge score would look at each unigram, each word in that scenario. And if the generated output matched it exactly, it would score at 100%. If, however, it's swapped, it is not cold outside, it still has the same number of unigrams, but the not is semantically changed that entire meaning of that sentence, but it would still get a pretty good score. So there are some of the kind of things we need to think about, and why I think using a combination of metrics is clearly quite important. Obviously, we've got safety and security, so bias, harmful and protected content, any indirect attacks that may be generated from the AI application is something that we want to look at. And then some of the newer techniques that are being used, custom metrics. So I really like this. So a lot of the AI quality and NLP metrics I spoke about are great if you're a technologist. They're looking at things in quite an objective way from a technology-driven approach, and looking at things such as coherence from a kind of a typical layperson view. If, however, we are in a really nuanced domain, such as law or finance, they will have certain terminology that is not common to everyday language. And it's really important to capture some of that training in how the model performs. So the Azure Evaluation SDK allows us to create custom metrics. And one of the things I've been exploring is how we can bring a lot of the people that will be using the solutions that we will be implementing into that process. So can they give us any kind of codification of how they would be assessing various different workflows in order for us to reliably measure that? And obviously later on, as they've been part of that design process, they're more likely to champion it because they have a bit more confidence in its abilities. And then lastly, simulations. So this is an idea borrowed from robotics. So Guardrails AI is a good example of this, but the GitHub Next agentic testing. So this is the research team that created GitHub Copilot, have been looking at the idea of continuous AI. So using agents to actually test different AI applications from a layperson perspective. Us as developers have created the features. We know how to use the application to get the best results. But obviously agents wouldn't have this unless you built it into them. So using agents to kind of simulate these workflows is quite an interesting approach. So this is the type of dashboard you can get. And we probably don't want to do this just for for AI application development, but also from an ongoing monitoring perspective. There are various different things and changes that could happen that is maybe not captured in the application we've built, and we want to look for performance drift. So we're at the point where we've got quite a good performing AI solution, and we're looking to deploy. So the GitHub Green Software Directory has mentioned a lot of different tools that we could use to start measuring the carbon impact, but also implementing automated efficiency. So in pink here, we've got tools like Code Carbon and Eco2i, which are looking at the typical hardware that's required to run a lot of these AI applications. We've got CO2JS, which is looking at our JavaScript code, understanding how much energy is required to transfer data over the internet. And PSE Electricity Maps, which is looking at the energy intensity of different Azure regions. And it's really great for simulations. If you're looking to change certain workloads at certain times, that's a really nice one to use. Cube Green gives you the ability to turn off any infrastructure that's not being used or just running idly. EcoLint, which is a static tool to start assessing your code, how it could be more efficient straight away. I know in the keynote there were a few others that were mentioned that could actually help you start doing a similar thing, looking at your code, making it a bit more efficient. Pruner, this has a lot of AI optimization algorithms built in. So you can definitely start improving specifically, or if you're going down the kind of fine-tuning route, absolutely consult that. And then EcoSonar, it gives you a lot of capability to raise awareness around sustainable development practices whilst you're developing. So I took a lot of these and I was like, great, so if I have my agent, my AI solution, I want to start building some of this capability on top. A lot of these tools don't actually look, they take the assumption that either you have a website or you're about to train a model. It's not from the perspective of, I'm going to consume an off-the-shelf model. So there is a bit of a big fat gaping hole. And when I started looking into this, sorry, that's a little bit small. I started looking initially at, if I'm making a GPT query, how much energy does that actually consume? So 3.4 watts relative to using TikTok, 66 watts, and Netflix, 12.8 watts is quite small. But at scale, obviously, that has a huge impact. And we're not just talking about globalized usage, we're talking about implementing this in the enterprise scale. And this is not even accounting for, obviously, a lot of the GPT and model training that energy consumes. So where should we start? Is the kind of AI training also our responsibility? I would say no, because we don't really have much controllability over that. So then I started looking at, okay, well, what about if I wasn't using GPT and I was using Claude or Llama or a different type of model? They're all much of a muchness, really. There are a few variations in there, but not massively. So what are we actually reliant on? We are reliant on a lot of the hyperscalers providing metrics such as power usage effectiveness, which tells us how efficient the data center technology is, and water usage effectiveness. So these are typically averaged over entire regions as opposed to one specific data center. So this particular blog, I'm happy to share the slides afterwards, looked at if we started mapping the entire life cycle of our AI development, how can we start measuring the carbon impact? So they made an assumption based on 105 billion daily requests going to GPT. Hardware and manufacturing, they calculated as being around 1.4 million tons of CO2. The AI training, quite low in comparison, at only 6,229 tons of CO2. And deployment adoption, which is our usage and the hardware, the energy required for us to use these AI tools. We need to obviously look at the kind of hardware required. We multiply that by the power usage effectiveness. That value is then times by the carbon intensity of the region. That gave us a whopping 45 million tons of CO2. So we add all of that up together and we're at about 47 million tons of CO2 per year to send all of our requests to GPT. Again, highlighting that the scale of deployment adoption relative to the hardware required to manufacture and model training is quite large. So this is the area of influence we could potentially have as developers. So this paper by Jegham et al. Actually looked at a little bit more of a pinpointed view. We know we can't control the AI training and a lot of the data center hardware, but if we looked at just that deployment aspect, they basically they were looking at the inference of GPT-4o, and they, again, made the assumption of around 1 billion queries per day across GPT deployments. They scaled for adoption rates, lengths of prompts, things like that, and came up with a figure of 391,509 at a minimum. So that's equivalent to around the electricity consumption of 35,000 US households, or more starkingly, the drinking needs of 1.2 million people. Given that drinking needs are still quite challenging for some people across the world, that one is a little bit harder to digest. So what data do we need to measure from our applications? We want to look at our API call latency or the tokens used. GPU or server energy draw, probably not going to be accessible to us, but we can make some inferences. And the requests per second or throughput. What data do we need to source? Power usage effectiveness provided by the data center or cloud provider, the carbon intensity factor provided by regional grids, and the water usage effectiveness, again, by data centers. So if we take these really complicated looking algorithms at the top and simplify it in code, what does that look like? So to get our total energy per request, we want to look at the compute needed to run each request times by the power usage effectiveness. If we take that output and multiply it by the carbon intensity, we'll get our total carbon impact. For water usage, again, we want the total energy per compute required. Sorry, the total compute required per request times by the water usage effectiveness to get the water usage numbers. So building my carbon agent. So as I mentioned, I've been doing a lot of work within the legal domain. This was a very low risk prototype idea that we were contemplating, the idea of a legal PA agent. So legal PA would do things like monitoring our email inbox, to kind of prioritize, define tasks that needed doing, and replying back to the user. It would have access to a few different sub-agents that had the ability to do things like summarize and draft emails, book meetings and meeting rooms, book travel, book lunch, etc. So it needed to be integrated with several different travel APIs and building booking systems as well. So I wanted to collect all of the telemetry from this agent, the tokens, the time needed to process, the cost, the task specifically, etc., and feed it to an agent, my carbon agent that I wanted to create. So I mentioned I'm using LangGraph, created a very, very simple single agent with access to 3 simple tools: carbon calculator, a cost estimator, and a carbon optimizer that could suggest various different improvements. So what does that look like? Let's go over here. Okay. Let me just make this a little bit bigger. Or not. Okay, I'm going to walk you through it anyway. So what we have here is some simulated telemetry. That was me telling you not to use 100% synthetic data, but we are for this example. So we've simulated our departments, we've simulated the tasks. So this legal PA agent is going over legal, finance, IT, HR, operations. It has all the tasks that I mentioned, and this is a huge law firm. So we're deploying across the UK, Europe, US, and even North Europe as well. So we've captured a lot of those static measurements that we needed, things like the carbon intensity, the power usage effectiveness, water usage effectiveness, and we've started to create some fake data. So some of the things that we have built within here is obviously already the total carbon for running certain processes in different regions. And likewise, we've done this with water. We can later transfer this over to our carbon agent, but for now it's in our synthetic data. So this is what it looks like. We have our event ID, our timestamp, our department, the type of task that we're doing, whether we're arranging a meeting, booking lunches, analysing contracts, etc. The number of tokens required, the duration, the region, and then we've got the power usage, along with our CO2 compute and our water usage, along with the total cost of that AI transaction. So feed this telemetry, which we have here, into our carbon impact agent. So we want to start defining our tools to start with. So obviously, if this was running in production, you could just directly pull the telemetry from your API. We've got the carbon calculator tool, the water usage tool here, which at the minute is obviously just drawing from the synthetic data, but those calculations can quite easily be translated in here. We've got our cost estimator and the optimization task. So we spoke a lot about personas and really clearly articulating within our agents what kind of persona are we trying to adopt, because if we are catering towards a sustainability officer, they are going to want data in a certain way that probably helps them to create their sustainability reports. if this is for a developer that is looking to optimize the efficiency of their AI solution, they're probably going to want much more pinpointed suggestions that are a bit more technical. So at the minute, we've just got some generic ones in here that talk about maybe changing the carbon region, caching certain responses, those type of things. So as I mentioned, the prompt is quite simple at the minute, but what we would want to immediately do is maybe say, this is for a developer, this is for our CFO, this is for our sustainability officer, or it's for an employee who is just who's quite interested in our impact from using AI. So I've bound those tools to our simple assistant here, and the mermaid graph shows that we would get an incoming request, it would use the relevant tools, and invoke the right messages. So obviously this is quite a simple approach and can get into a lot of recursion type problems. So I've set a limit of 50, just so we don't infinitely keep calling different tools. And I've asked the very simple question, what is the carbon footprint and water use of our draft response tasks? So it's gone through, and as we can see, it's taken our human message, it's called various different tools to understand what was the task that was done, what was the carbon associated with that, and quite neatly kind of reported back, this is the total carbon usage, and this is the total water usage. Now, as I mentioned, if we are a developer, we probably want to integrate this output with some kind of monitoring dashboard. So we can start prioritizing what things do we need to start looking at. And this is just for one agent. If we start thinking about a lot of the shadow AI that goes across organizations, we can start looking at, well, how much duplication is there actually? And that's a lot of kind of where we can target those quick wins. But if we're an employee that's just a little bit curious, we're probably all a little bit chatbot to death, but I've created a very simple chainlet application here, which enables us to obviously start interrogating that data as well. So we can ask how many emissions are associated with draft responses. And as we'll go on to see, obviously, so that's given us the very simple answer. If we want to know how can the emissions of draft response be reduced, what we'll see is obviously we haven't given our agent any kind of detailed targeting blueprints around what are the kind of approaches based on risk appetite, etc., that we can use to implement and automatically improve the efficiency of our application. So we're going to get back a lot of generic type of spiel, which if you're looking at this as an employee that's maybe not technical, that can be quite overwhelming. Just give it a few moments. Yeah, there we go. So prompt and token optimization, model and runtime choices, data center and region selection. So a lot of generic information in there, as mentioned. But as organizations, we probably want to start thinking about, well, what are the blueprints that we want to adopt in order to, and they'll probably be from various risk appetites or also through to effort required to start implementing all of this. So if we go back, what are some future improvements that I would want to make? So more agents, as I mentioned, within law specifically, they have many different practice groups. The AI literacy maybe isn't up to par. They've typically been quite risk averse and slow to adopt new technology, but the enthusiasm and excitement for adopting AI is definitely there. But that's obviously led to a lot of duplication, as mentioned. So if we're going to move towards these world models that can holistically use data from across all of our different practice groups, we definitely want to look at what else is going on. Besides the legal PA agent, we'll have things around mergers and acquisitions, we'll have things related to criminal law, Most of those practice groups will definitely want to probably all do some level of research and e-discovery. So that could probably be a genericized tool across the law firm rather than having several different versions. And then we've got the risk data I mentioned around enrichment. So if we are making judgments around or drafting memos of advice for criminal law, there is a certain level of risk attributed to that we perhaps want to most definitely have human in the loop at every single check mark before we go and release that to a client, versus the legal PA agent, which obviously it's not particularly professional if we get a meeting wrong or something, but the risk is definitely a lot lower. Automated remediation. So caching is definitely something that we've already started to implement, where things are asked multiple times. We can just have that kind of stored, ready to surface when it's asked. Prompt rewriting, obviously pretty standard practice these days. And persona expansion. So I mentioned a few different personas, from our sustainability officer through to our technical dev, through to our CFO, and even our employees. So developing more personas within our agents enables it to perform a little bit better. Obviously, adoption and usefulness of those applications can also improve. So I've talked a lot about kind of the hardware and the software aspects of what we can do, but hopefully you can see that scaling AI is both a software and a hardware issue, but when we design it effectively, the benefits are pretty profound for the planet as well as performance and profits. Thank you. I'll be happy to take any questions.